My name is Brian Robbins, and I come from Microsoft. And today I am going to talk some about how we do performance diagnostics for .NET applications on Linux. So just the brief summary of me. So I'm a developer at Microsoft on the .NET reliability and performance team. So our team is responsible for performance of the entire .NET stack, all the way from the runtime all the way up through applications. And so today, just a brief agenda. I'll talk quickly about what .NET Core is. Talk a little bit about the difference between what we call managed versus native applications, how we capture performance tracing data. I'll do a couple of demos and talk about what works and what doesn't work, and then touch on a couple opportunities for future improvement. So before I get started on talking anymore, I just want to do a quick hand raise poll. So raise your hand if you've done a performance investigation. All right, that's good. Lots of people. So raise your hand now if you've done a managed perf investigation. So Java, Python, .NET. All right, so a lot of people. Okay, of those people, raise your hand if you've ever had trouble getting stacks or symbols for managed code. 1, 2. All right, that's good.
It's a great tools.
And then then raise your hand if you've ever tried to understand the behavior of runtime components. All right, we got a few. So things like garbage collector and just-in-time compiler. All right, so this talk is all about how we do these things for .NET on Linux. Though I can imagine that at least a decent amount of this information would apply nicely to other managed languages as well. So our goal as the .NET team is to enable use of existing Linux tracing tools to understand the behavior of .NET apps. So we're definitely not in the business of wanting to reinvent the wheel. And so that said, as we go through the talk, if you know of something we can do to improve, we want to know about it. And so in fact, at the end of the talk, I have my contact information. If there's time at the end, I'm happy to talk to. But please do reach out to me if you happen to know of something we can do better. Okay, so .NET Core. So .NET grew up on Windows, but now it runs on Linux, Windows, and OS X. And so .NET Core is the product that allows you to write .NET apps that run on those platforms. Whenever you write a .NET app, it is compiled down to what's called MSIL, Microsoft Intermediate Language, which is then compiled to native at runtime. So we call that code managed code. .NET Core is completely standalone, so it can be packaged with your app. You don't have to install it. You can have as many versions of it as you want on any given system. It's completely open source, so that's the runtime, libraries, compilers, languages, and the tools. All open source, all developed on GitHub. .NET Core is supported in production by Microsoft, and the lowest piece in the stack is called Core CLR, which is the runtime that's responsible for app execution. So a little bit of information on the differences that we see, at least, between managed and native applications. So managed apps are basically native applications with some additional services. The first being the fact that we have managed code. So this is code that is not compiled down to the native representation. There's also services like garbage collection, just-in-time compiler. Some managed stacks have an interpreter, interop, which is being able to make calls from managed to native code or back. And all of these services need instrumentation and or special handling in order to actually understand what their behavior is. So we have a script that we use called perf collect. It's a data collection script that we use for all of our Linux perf investigations. Its job is basically to install dependencies for any new users. It's responsible for enabling and disabling the traces we use. And the idea is to make it real simple. So it's got a good set of defaults, and it's got specific modes for particular types of investigations. And what it does in the end is it produces an archive that contains everything we need, trace files, managed and native symbols, and anything else to do an investigation on a different machine. So the idea is that we can hand this off to anyone and say, oh, if you collect some data, hand it back to us, we can take a look. So before I go any further, I want to just do a quick demo of a CPU flame graph. The idea here is that we'll use perf collect to collect CPU clock events via perf, and we will enable Gzip compiled code symbol collection via the existing perf mechanism, and then use Brendan Gregg's flame graph tools to generate the flame graph. And the nice thing about this is that we really didn't, you as the user don't have to do anything special, and we haven't really written any special tools or anything to make this happen. All right, cool. So you guys can't see that. Oh, all right, we're gonna try another experiment here. That's better. Okay, so for the purposes of the demo, I've written a demo script, and the idea of this is that not only can I not type a bunch of stuff that ends up being incorrect, but also this is reproducible for anyone who wants to try it after the demo. So what this script will do is it will collect a performance trace. Under the covers, it's going to use perf and LPTNG, and it will zip that whole trace up. And then it will create an on-CPU flame graph using the data collected from perf. So the first thing it tells us to do is set up some environment variables. We do have a few environment variables that are required to turn on tracing for the runtime, and they are things that we want to get rid of that we're working on. And I've also got a couple other in there that are for the purposes of this demo. So now what I'll do is go ahead and run, or get myself set up here to run the actual test. All right, so
is the font size okay for everyone?
No.
No.
Make it larger.
I have not been able
I see lines going across,
You see lines going across.
which I think is text.
It is text.
Just tell us what we're seeing.
Yeah. So what you're seeing at the bottom here, or not seeing at the bottom here, is that's the command to run a serialization benchmark. It's basically something that we wrote a while back to compare some serializers. What I've done at the top here is started collection, and so all it says here is collection started. So I'll go ahead and run the app. So there are a handful of serialization frameworks in the .NET framework. And so basically what this does is it runs a whole bunch of them doing the same thing, and then we can compare the results. So now that that's done, I've stopped tracing, and what it's doing now is collecting all of the symbols, both native symbols that are available, collecting the trace files and zipping them up. And so if I hit enter on that, now what it's going to do is create a flame graph. And so before I bring that up, this is a very large flame graph of the same exact benchmark, but it does not have any managed code symbols. And so what I can see is that the bulk of the time was spent in main, which is this very large section in the middle. But as soon as I get to get beyond these native frames, everything becomes perf-pid.map. So you can't actually tell what it's doing. And in fact, I can scroll all the way up, and all those things all say the same thing. So it's really quite useless. All I know is I had a really deep stack somewhere, but I have no idea what it did. So it's the classic I don't have symbols problem. But we do have native symbols. So now, if I come back around, so in my results directory here, I have a flame graph. So now, bring that up. So still pretty deep stacks. And you can see the same exact beginning of the stack here, right? So the bottom of the stack is all this, is the main method and the host loading the application. But then we very quickly get into managed code. And so we can actually see that the first frame here is called serialization comparison main. So that's the main function. And on top of that, there's 1, 2, 3, 4, I feel like there's even more than that. 5 different serializers that we compare. And we can tell, relatively speaking, how long they took comparatively based on their width. And in fact, if I click on one of them, and this is a particularly large flame graph, and so it takes some time, I can now scroll up a little further, and I can see exactly what happened. So all of these frames, or the bulk of these frames, are all managed code, and I can actually tell what they're doing. On the right-hand side, for example, all this stuff, you can read it, says Microsoft generated code. So that's all code that was generated on the fly by these serialization frameworks. So without these JIT compiles, then we'll have no idea what it's doing. All right, so we'll come back to the slides.
For the Microsoft generated code, do you have any idea of what the source is?
Yes. Wow, that did not work. I will fix that again. Yeah, so the source code for that lives in the .NET framework. And basically what it's doing is it's creating, so when you create the serializer, one of the assumptions or hints that you can give it is that I'm going to be holding onto the serializer and using it over and over again. And so what it does is it basically code spits a custom crafted serializer for your document. All right, you guys can't see that. Let me see if I can fix that. Okay, all right, cool. So kind of moving backwards in time, .NET grew up on Windows. And so we have built a whole ecosystem of tools on Windows. And our goal is to be able to go ahead and bring those over to Linux. So we started off with using just Windows tools. So the tracer that we use on Windows is called Event Tracing for Windows. It's a high-performance logger that's built into the operating system. It does machine-wide traces. It can give you information about CPU, context switches, kernel and user mode events, and you can get call stacks with each of them. Symbols are all handled offline. So when you collect a trace and open it in an analyzer, the analyzer can download the symbols using what's called the DLL signature, which is kind of just like a building. So what's nice about this is that we get one trace and it spans kernel, runtime, libraries, and the app. And so we wanted to try to do that on Linux as well. So our goal on Linux is to enable analysis techniques from Windows using the Linux ecosystem. And so after some deliberation, we chose to use perf and LPDNG because both have similar functionality and goals to ETW. They're both machine-wide. They are both event-driven, and together can provide us with kernel and user mode information. And we can get some call stacks as well. So why both? So it turns out they each provide us with a little bit of different functionality. So perf can provide us with a sample-based profiler with call stacks, so we can use that to understand the arbitrary code behavior. We can get kernel events with call stacks, but it doesn't support user mode trace points. And LPTNG, on the other hand, can provide us with user mode trace points. And so we actually have the runtime instrumented throughout so that we can use that to gain further insight. And LPTNG also provides both persistent and real-time traces, which can be used for analysis and monitoring. The one thing that we're missing on user mode trace points right now is stacks. So by default, we collect 3 different types of data. We collect machine-level data, so things like CPU samples and scheduling events. We collect runtime data, so these are things like managed object allocations, statistics about the garbage collector, statistics about the just-in-time compiler. And then we can also collect managed code instrumentation. So these are app-level types of trace points, so things like start and stop web requests. So whatever a framework wants to instrument so that it can use that data. And so here's what we can do today. So using Linux tools, we can do resource analysis, so that's things like CPU and block time. We can do managed runtime event collection, so we can collect a whole bunch of events that are instrumented throughout the runtime, and anyone can write their own analysis scripts on that data. And then we can also do GC and Gzip reporting, so we can get fairly detailed information about what the garbage collector and just-in-time compiler can do. And if we're willing to take that trace over to Windows, we can do a little bit more. But our goal is to basically remove that gap so that I can take the Windows tools off of this slide. So now we've seen a demo of a flame graph of a .NET application. So what I'd like to do is kind of walk through some of the internals, some of the things that we had to do to make all this work. So the first problem that we ran into was stack blocking, and we found that for the most part we were getting broken stacks and stacks that we didn't trust. And so the first thing we did was we started compiling all of our native code with fnorm and frame pointer. So we do take a small performance penalty on that, but for the benefit of being able to actually do performance tracing across the stack. We've also modified our Gzip compiler so that both online at runtime and offline pre-compilation of managed code preserves the frame pointer as well. The experience is still broken sometimes. All it takes is one library not preserving the frame pointer, and we know that there's lots of them that do that, so it's not a new problem. The next thing that we had to do was attack symbol resolution for managed code. And so we do that today using the existing perf mechanism, which is you stick a file in the temp directory, and that file contains information about any managed code that's been compiled, any Gzip compiled code that's been compiled in the process. And so an example of an entry in there is sitting right here at the top. So in red, that's the code address, the start of the method. Green is the size, and then blue on the right is the symbol. And so perf knows how to handle that automatically. We just emit the file at runtime. One of the sticking points that we run into here, though, is that we do have a pre-compilation strategy. Sometimes it is not desirable to be compiling all of your code on the fly at runtime, and it can certainly impact startup. And so we use a cross-platform file format, which contains the MSIL, metadata, and optionally pre-compiled code. And so it's not so easy for us to convert to ELF, but at the same time, we can't use the JIT of that map file because perf knows that this is not JIT compiled code. It knows it's coming from an image like this. And so what we do right now is we generate map files for all of our compiled code, which gets used by custom tools. But that's certainly something we're looking for ways out of. Yes.
Do you have any issue with, do you reclaim memory from Gzip compiled code?
Very seldom, but yes, and that is one thing that we're aware of. So there is another patch that I've seen out there which allows you to handle load and unload, but it's not something we can use based on license. So we're MIT licensed, and so the patch that I've seen out there is all GPLv2, and so we're not able to use it. So the answer is yes, but very seldom. So it doesn't affect us much.
Because you could, with the LTTNG UST side, you could book into the beta address load, download of library type of events, and perhaps if we need to extend that to books for JITs, so that they can tell the tracer that they're actually mapping and unmapping code from memory, that it might be useful there.
Yeah, that would be interesting. Thank you. And so the third bit of internals that I wanted to cover on this is also symbol acquisition. So on Windows, we're used to just downloading our symbols from a symbol server. It's also true that Gzip compiled code can't have full symbols on pre-created just because it's created on the fly. So we do collect that in the runtime. On Linux, we have moved to a strategy where we collect all the symbols that we can at runtime and put them in the trace file. So for native symbols, we actually leave function names inside of the binary. but we strip all of the rest of the debug information out, and that can be downloaded manually for debugging. For managed code, we generate it all at runtime, so there's the perf-dev.map, and then there's the offline utility that we use for recompilation. We generate those files as well, and they all get zipped together. So in the future, we'd love to see a symbol server mechanism on Linux. It's something that we've seen a little bit of chatter on, and so we're looking for ways to participate and potentially proposing an option. All right, and so the second demo that I'm going to do is the demo of how we do, at least how we start off with GC engine analysis. So this uses another side of the instrumentation. So this uses LTTNG trace points. So the runtime is littered with these LTTNG trace points that log information about various runtime services. And so all of that data gets emitted by LTTNG, and then we read it in with an existing tool called Purview that we've ported, we've started porting from Windows to Linux. It's a .NET application, and it actually knows how to read CTF and generates reports based on that data. All right, so I left everything where it was. We've created the flame graphs now that enter again, and this thing now is going to go create reports. So we already have a trace file. So that trace file contained both perf and LTTNG data. And what I've done is gone ahead and run using Purview. I've gone ahead and run through various configurations to tell it to please create what are called GC stats and JIT stats HTML reports. So I'll pull those up. All right. So this is the GC stats report. As you can tell, we're not nearly as good with UI, but it has the information we need, so we'll take it. So this is the kind of report that we generate. We can generate this both on Windows and Linux. The trace points that show up are the same. The information that comes out of the runtime is the same regardless of platform. And what this lets us do is do a bunch of aggregation, statistics generation, and get information about the garbage collector. So this table at the top is a per generation roll-up. Basically, how many collections occurred during the trace, and a bunch of statistics about that. I'm not going to get into too many details about what the data is, but other than to point out that it's not so easy to generate this data on the fly as you're going. Much of this is done in post-processing. And so now if I wanted to, I can actually dig into each of the collections. So I can know when it started, which is this pause start column. I can understand why. So what triggered the collection? Generations, how much of the heap was collected, how long the runtime was paused for, so on and so forth. There's a good amount of data here, but the idea is that folks who work on the garbage collector can understand exactly what's happening with this kind of data. In fact, this is even though there's a decent amount of data here, this is actually a small amount of what's available. We can actually generate even further raw information to really try to dig down further. So we do this as opposed to using something like a debugger or dumps, because we can understand the data, we can understand the behavior over time, and we can see how the garbage collector is changing behavior over the application. There's also some other information down here as well, which is called the condemned reasons table, which is responsible for telling us why a collection might have occurred. Most of these are zeros. A lot of the time, that's pretty common, but occasionally something gets filled in and it tells us something useful. For example, collection number 7 started off as what's called the Gen 0 collection, so it's only going to collect a small part of the heap, but the garbage collector decided it actually needed to do a Gen 2 collection, and so that's what it did. And it actually tells us why. It says that the Gen 2 generation budget was exceeded. So we can use all that information to understand the behavior. without having to start digging through data structures or looking at raw events. The other report that I want to show is called the JIT stats view. Same great UI, different information. And what this one does is it shows us how much JIT compilation time occurred during the trace. So in this trace, we did JIT compilation for just over 2 seconds. That is really bad. I did that on purpose so that this would actually fill out the report, because it's pretty common that we hit a lot of precompiled code. We keep all of the framework precompiled. But what we can see here is how long things took, how many methods, input and output size, and same thing as the GC view as well. We can get down to individual methods, when they were compiled, how long they took to compile, input and output size, and the method signature. So you can know exactly what was being compiled. And so this is actually really helpful if you're looking at a trace and discovering that the just-in-time compiler happens to be something that is on your hot path or bottlenecked, and you can understand exactly what's being compiled, and then you can go make changes to your code, whether or not that's pre-compilation, whether or not you're using something that happens to be expensive from a compilation point of view, etc. And in fact, there's more data which isn't collected here, but we can actually get detailed inline information as well. So whether or not a particular function is inlined in a particular code site, why or why not. And so we can use that to understand behavior. It's all pretty. A lot of this stuff gets pretty detailed, and so these are very useful for both arbitrary, both .NET developers who want to get into performance, but also for our team as well. So just to go through a couple of internals on how we did that as well. So as I said, .NET comes from Windows, and now we're on Linux and OS X. So we need to be able to send our instrumentation to different tracers based on the platform. So today, Windows data goes to ETW, Linux data goes to LTTNG. In order to do that, we basically we use build scripts at build time to generate trace point definitions, and we actually have stub functions that log them. So these stub functions are littered all around runtime, and we just generate them to have them call into LTTNG specific code on Linux. So the other thing is that some runtime services are implemented in managed code, and applications can add their own events as well. And so unfortunately, right now, what that means is that all that managed code instrumentation funnels into one trace point, because it's not yet possible to dynamically register trace points. So we get into a situation where we don't have any way to create the native trace point code at runtime, and so what we do is we funnel that all down to one. We've got some filtering capabilities, but they're fairly minimal. So that's something that we're looking forward to attacking at some point as well. And then another thing that I wanted to talk briefly about is how we consume. So this is a .NET application. So Purview is a .NET application, but it does actually know how to consume CTF traces. So Purview contains all this custom report generation code. It's stuff that actually predates .NET Core running on Linux. And so we have this underlying trace reader called trace event. And it grew up in a different world. It grew up in a parallel world from Linux, so not to be confused with trace_event. And what it does is it reads multiple trace formats. So it knows how to read ETW, it knows how to read CTF. It actually can read some kind of custom XML formats. It can read some others as well. But it exposes a standard consumption API. And so we build tools on top of that. In fact, Purview is built on top of that. One of the other nice things is that in addition to handling files, it also knows how to handle live sessions. So we can do monitoring of .NET applications using trace event. And I'm not going to say any more on that because that's actually what's coming in the next session. So just to wrap up, a few opportunities for future improvement. I think better support for JIT compiled and precompiled cross-platform code would be great. Mostly, our pain has mostly been around symbols. collection of stacks for user mode trace points so that we can understand the behavior of runtime services that need to instrument themselves and would benefit from the stacks. An example of that would be object allocations. If you have managed object allocations, today we can see types and we can see counts, but we can't actually see where and what code allocated it, other than the fact that we can get the IP, but we don't know how we got there. And then dynamic registration of trace points so that any arbitrary managed code, whether or not it be .NET code, Python, etc., can generate its own trace points. So coming back around, our goal is to enable the use of existing tracing tools to understand the behavior of .NET apps. And so if you know something we can do to improve, having just sat through that talk, I would love to hear about it. So I've got some resource URLs here as well. These are available online. If you want to look at any of the demo code, want to know how to do tracing on for .NET Core, etc. And if you want to reach out to me, that's my info. All right, thank you.
Questions for Brian? Well, I have one of my own. Regarding your wish list, you said dynamic registration of trace points. Would it be okay? I mean, do you need also dynamic unregistration, or it's okay if their lifetime is basically, ends with the end of tracing? I mean, because for LTTNG UST, for instance, given we keep a registry of everything that needs to be in the metadata, even if you unload some code, I mean, that event ID and everything would still be there for the active session. Is it a limitation that's unacceptable for you, or is it okay?
It is likely acceptable. For the most case, code does not get unloaded, so it's not an issue. It can be unloaded, and so if it were unloaded and reloaded, the key would be to make sure that it either took over that existing slot or created a new one, and it would be fine for a parser to have to know that there are multiple.
All right. Other questions? Yes.
Hi. About this trace event tool, is it open source?
It is.
Okay.
It is open source and it's on GitHub.
I'm just curious about what language is it written in?
It's written in C#.
Okay, so you use a custom reader for CTID?
Yes, it is a custom reader. And in fact, that was one of the things I wanted to talk about today, potentially with you and Jeremy, is the fact that we'd like to use Battletrace instead of our custom reader.
Yeah.
I'm right there with you.
Should be doable starting from 2.0.
All right.
All right, thank you.
Thank you.
Other questions? Oh.
I didn't get if Purview was also open source or.
Yes. Yes, it is open source. Yes, it is open source at the bottom here. It's developed on GitHub.
It runs.
We have started porting it over to Linux. So the bulk, if you've ever run Purview on Windows, the bulk of it does not run on Linux yet. But we are looking for ways to start porting more of it. The bulk of the pain is mostly in UI, not because it uses Windows UI specific frameworks. But the idea is that because most of the trace processing is all based on the trace event library, as long as you use the standard consumption APIs, it doesn't matter what trace format is underneath it. And so we've started porting that functionality.
And does it scale to very large traces?
It can, yes. I've not tested very large traces on LPTNG. On Windows with ETW, we scaled at about 1 gigabyte, but I don't think that's like 1 gigabyte is where things started to get big, started to get slower. But I don't know that that's necessarily a comparable thing with LPTNG, just because the formats are different.
Thank you.
Yeah, just as a matter of comparison, I mean, the LTTNG tools, the graphical tools, we typically more target tens of gigabytes worth of trace data. So perhaps there might be some ideas to look into and to read.
Yes.
Other questions? Okay, thank you.
Thank you.